Hello and welcome to Computer Tech and More. Today we're going to be doing part of my Redone series, and today we're going to be taking a look at the Squama 2503. This is the B edition, in other words, black. Let's get into what I'm going to talk about. So as part of my Redone series, I did a complete reanalysis of my noise testing methodology. So originally I placed the microphone really close up to the fan and just tried to cancel out as much of my room noise as possible because I'm just in my office and have no real noise isolation to it. So I figured that would be a good way to test. In hindsight, it was giving me wind effects that were going across the microphone itself. And I was getting interaction between the fan blades and the microphone outer layer as well. So as a result, I think I was getting up extra resonance going on. I'm not a noise expert, but I think some interaction was going on and was causing me to get peaks of noise that really don't exist in the fan itself. A better way to do that that I should have done was actually place it closer to the hub as opposed to the edge. But now I have a fixed distance that I'm placing the microphone from the fan itself, where I have a stick to measure it so it's exact every single time, and this stick is only for doing my noise testing. And I went from a plus or minus 4 decibels, so that's an 8 decibel range for accuracy, to a plus or minus 2 decibel range. And furthermore, I'm increasing the consistency of the testing, making sure that my house, home, and environment is within the same decibel range of plus or minus 2 decibels every single time for every single test, while before I just kind of whatever was going on. So overall, just increasing the consistency for my noise testing going forward. Well, I might as well make this point here. To further increase my fan testing and make it as good as possible, I really can't do it without viewer support, either subscribing to my channel or it would be beyond belief for me, joining me on Patreon and any level, because I want to upgrade my microphone to one that's dedicated for sound testing. Right now I'm just using the one that I'm using to record my voice, which is good for peak levels, but not as great for seeing broad spectrum. So I want to be able to get you guys the most accurate data possible. I want to build myself a little sound box. So they have like this special insulating material that absorbs sound, as well as it's sort of like drywall, except it's designed to absorb sound. And I would build it out and then put the testing apparatus inside of it, and it would absorb all the outside sound, so it would greatly drop my threshold for noise so that I could pick up, well, just the sound of the fan much more accurately. I want to get a better anemometer, one that's a bit more accurate. So instead of being plus or minus 0.1 meters per second, one that's closer to 0.01 meter per second. And I think I found one that lines up, but it's like $500. And all that's just a little bit hard to justify right now. But if you would like to join me, help me out, or just sign up, or just subscribing to this channel, and eventually YouTube will help me out a little bit, I'd greatly appreciate it. So anyways, let's get into the testing that I did. So first up, my testing was the original testing methodology and all the fans in the 120 millimeter class category, with the new testing methodology with all the fans. And they're done alphabetically, so they all line up side by side. You're going to have the fan model number, the RPM, and its airspeed or CFM. There's going to be a little shortened label for what the test was and how it ranked in my original testing methodology versus the new testing methodology. And note, my noise normalized testing got a different noise normalized value, but it's related to the same fan RPM as before. So it's based off of the A12X25 running at between 1,100 and 1,200 RPMs. And originally it was like 40 decibels. In the new test methodology, it's based off a 12 decibel mark. That's just how much noise difference there is between having it right up against the fan and being a bit further away. And I do want to make one thing clear. My old testing methodology is not completely invalid. It's just a much more limited use case. So its use case would be if you had a mesh filter or the grate of your case right up against the fan. Then you'd pick up that extra harmonic sound that I ended up picking up in my original test methodology, or in a more similar to a pull configuration on a CPU air cooler, or potentially a radiator, whether it's an AIO or a custom loop. But I feel the new test methodology is more closely related to fans blowing from the front of a heatsink, blowing it through the back. More cases with radiators in a pull configuration, because usually you're not going to have the fan right up against the fin stack. And more cases these days where the mesh filter is spaced out from the fan a little bit to allow that air gap, so it's more efficient at drawing air into the fan, as opposed to having something right up against it where you're not going to get as efficient airflow going through it. So first up in my testing methodology was through the cooler, noise normalized, and the Squama 2503 was originally ranked 36th. It is now ranked 37th. However, its overall airspeed has increased, which is actually a good thing. Despite it dropping in position, relatively speaking, by one place, it actually increased in performance. So that means it's actually better at moving air than what we originally saw. And ironically, it actually dropped in RPM. So that's kind of interesting. Either way, the ranking is what the ranking is, and I remeasured all this during the testing, so it's just kind of funny. Are we done on this one? Next is cooler at 100% PWM fan signaling. This one, positioning is not going to change because it is not, noise is not the factor. But the Squama 2503 was ranked 22nd. And you have the RPM, the noise level it was seeing. You're going to notice a difference in noise level, and that is just because of the difference in test methodology. And the air speed. Next is the cooler value proposition. This is how much performance you get per dollar. And originally it was ranked 36th. Now it's ranked 26th. So it went up in value with comparison to the other fans around it. Next is cooler at 100% value proposition. It's ranked 23rd overall. Next up is CFM testing noise normalized. It was ranked 28th overall. It is now ranked 35th. So it's an overall drop in position, and we do see a drop in CFM value. So it produces less airflow for the same amount of noise in this particular test. Next up is at 100% PWM fan signaling, and it's ranked 22nd overall. Next, we have the value proposition for CFM. The Squama is ranked 26th. Originally was ranked 26th and is now ranked 23rd. So overall, an improvement in position in its value proposition, noise normalized. At 100% PWM fan signaling, it's ranked 25th overall. Next up, we have my case simulation test, noise normalized, at the 6-inch mark. Originally, it was ranked 23rd. It is now ranked 31st. As a general note, if you're familiar with my channel, you can just watch this and carry on, unless you want to rewatch my analysis, which I would encourage you to do, actually. But you don't need to. And if you're new to my channel, I encourage you to just skip to the actual testing methodology, and I'll go through how everything was calculated, why each section is important, and how to select the fan that best suits your particular set of needs, and then you can review this and see where the fans rank for that particular purpose. So did I do the 6 mark? 20 went from 23rd to 31. At the 11-inch mark, noise normalized, it was ranked 22nd. It is now ranked 26th with an overall loss in airspeed. Again, noise normalized. Next up, 6-inch noise normalized value proposition. It was ranked 22nd. It is now ranked 21. So overall, a slight improvement despite a drop in its perceived value proposition. With the 11-inch mark, noise normalized value, it was ranked 24th, is now ranked 19th. But again, we see a slight drop in its overall value proposition. All right, let's get into the data on this fan. So one thing I wanted to get into before I get into the actual data is the science that Squama is trying to utilize on the fan development, and I didn't have this picture in my original testing analysis. So these dimples, they're supposed to be doing something like what you see on a golf ball. So this is representative of the airflow around it. So without dimples, you get this huge area behind the ball where there's vortexes spinning. Actually, it wouldn't be one big one. It would have one on the top and one on the bottom. If you can imagine in 3 dimensions, it would be coming from all sides, sucking in towards the middle, and it would be slowing it down because it has this big pressure area, because the air isn't sticking to the ball, because the air is in a pure laminar flow which wants a specific shape for the air to stick to it. While if you have dimpling effect on the ball, this trips the air to turbulent and helps hold the air close to the ball, so now you have a much smaller area, so a much smaller vortex of air that's basically going backwards in the wrong direction that would slow down the ball. It's the same sort of concept that you can imagine if you ever have been behind a big truck. You can get an increase in your gas mileage if you fit into its slipstream. And this is because the air behind the truck is trying to fill in that gap. It creates a small vacuum behind it and helps suck your car forward. And the closer you get, the more efficient it gets. Of course, you want to stay safe and not get too close. Mythbusters actually did a whole test on this. So if you want to see the science, I encourage you to look at Mythbusters. They did the golf ball test and the behind truck, and that is essentially what Squama is trying to do with their design. And it's hard to know if the effects are actually effective or not without having a version of this fan that has no dimples on it versus one that does have dimples on it. So you just have to trust that they know what they're doing. But either way, I think it looks cool. Let's get into the graphs. First up is my case simulation test. The case simulation test can be looked at in a couple key different ways. The first one is, what size case are you actually planning on buying? And how do you plan on using the fans within that case? So for example, the 6-inch mark is representative of a small form factor case that is still a front to back airflow. So in essence, it would be a little bit larger small form factor, while the ultra compact small form factor cases like the Fractal Design North, where the fans suck in from the sides and blow out the top, or blow in from the bottom and have to go through all the components and then go out the top. Those are more like a pressure application. So you would actually look at the data for how the air ran through my CPU air cooler, or how they did in CFM testing to determine if that would be a good application for the fan that you want to use. This wouldn't be the ideal data for that. But a larger, smaller form factor where the air goes front to back in a more clean, standard, like a full tower case, airflow would be applicable to it. The other application for the 6-inch mark would be fans on the bottom of your case, something along the lines of the Fractal Torrent would be that 6-inch mark. So the fans are all lined up on the bottom of the case and you're blowing them straight up into the GPU. That would be a good indication of performance at the 6-inch mark. If you're getting a little bit bigger case, a compact tower, the 9-inch mark would be your key point that you'll want to take a look at. I don't have any cases on my mind that fit into the 9-inch category, but just think probably one that standardizes out at MATX, micro ATX, as opposed to most ATX cases, and it would certainly be a bigger case than what you would fit with an ITX. The 11-inch mark would be what I would consider a standard mid-tower case, something along the lines of the Corsair Stormtrooper case. I just don't remember the number of it offhand. The Corsair 550D, the Fractal Meshify 2C, or some of their other mid-tower size cases would fit into that 11-inch mark. And the 14.5-inch mark would be a big tower, something like the Fractal Design Torrent, which is a case that I have. And I took measurements of a bunch of different cases from what I could find online and measured out where the CPU cooler would be. So this is, every case is slightly different in sizing, but these are good generic ballpark numbers where most cases fit into values close to these. The other way to take a look at this data is how good is this fan at actually blowing air efficiently. So the most perfect fan idealized in the world would be it would have no air loss drop from the front of the case all the way to the back of the case. So that means the cylinder of air that the fan produces would be maintain speed throughout the entire case. Unfortunately, that doesn't happen. This graph shows off actually a ceiling fan, so it shows off pressure and airspeed. actually airspeed. So airspeed will slow down at the edges first, and it causes the air to spread out. And it's pushing the air out of the way, and that's why it's slowing down. So you're never going to have a perfectly flat line. So you want it to be as linear as possible, straight line, and as shallow a drop as possible. What you don't want to see is a steep drop off and then it level out at basically 0 meters per second. And then this brings me to how does the air flow? So if it drops off to 0 very quickly, it's going to look like this generic old-fashioned style static pressure fan. I personally think that all fans should be this tight, concentrated airflow because in static pressure scenarios, it's going to fill the space anyways. So might as well just have a fan that is as versatile as possible. But when it spews air off to the sides, it fills a volume of air really well, but the air is not traveling forward through the case very well. So in this case, you really want one to have a good concentrated airflow for your case fans. For radiators, heat sinks, whatever, the airflow pattern doesn't matter as much, but you still need to have enough airspeed to get through it. Where it does matter for when it's hooked up to a radiator is if you have it in a pull configuration, so your rad is over here where the air gets sucked in and the fan is on the backside, because the flow pattern coming out the fan will be the exact same whether it's in an open air environment, so it's at the front just blowing air in, or if the radiator is the piece in front of the fan and the fan is at the back. So a pull configuration that Linus from LTT always talks about. The other key thing with that is if your radiator is on the back side of the fan, so the fan is blowing the air through it, the radiator or heatsink naturally is going to straighten out the airflow coming out it. So the air is going to actually come out looking pretty smooth on the back side of the fan, but you'll still notice the airspeed dropping over time, but the air will be in a nice smooth pattern. So this case airflow doesn't really matter as much if you're going to go AIO or custom liquid cooling if you're looking at it from the front. What this is mostly applicable to is if you're doing an air cooler, because you want to have the maximum amount of airspeed hit your air cooler as possible so that it doesn't have to re-accelerate the air and try to get out the case. You just want it to be a nice, smooth, steady flow pattern to get the air out of the case. Now, after all that said, I have just some key data points. I actually took it at every 10 power PWM signal intervals, but this is the 20, 40, 60, 80, and 100% PWM signals with trend lines, not the actual line. So you notice that the trend line can't quite match up to this because it's got a sort of slow and then steep drop off and then it levels out. So let's actually get right into my next graph, which is noise normalized distance from the fan versus airspeed versus my control fan. The control fan here is in teal, while the Squama is in red. So the Squama starts off looking pretty well, and then it just steeply drops off in airspeed. Already 120 millimeter class fans have a steeper drop off than most 140s, but for the Squama, it's actually very dramatic. So as a result, I would say it's not really that good of a case fan if you're looking at anything over the 11 side. So in other words, I'm talking about mid-tower cases. How do things look at 100% PWM fan signaling? Well, we're noticing something similar going on. It drops off steeply in performance, and then it's lost as much performance as it can, and it kind of starts leveling out. As a general note, with my current anemometer, it's hard for me to get good airspeed readings at anything less than 0.5 meters per second, which is why I'd like to upgrade it. But again, I need help from you, the viewers, or I need some sponsorship help. Anyways, I'd say the Squama is an okay pick for case fans if you're talking about a small to I don't want to say medium size, but maybe a medium-sized case, a smaller medium, if that makes sense. Next, how does it compare against other fans in the 120 millimeter class category? Well, the Squama is here in purple, in a bold purple. We have the Gentle Typhoon, which was one of my top picks in my previous testing methodology, and it retains its position. However, it doesn't look quite as good as it did previously. And we have like the Silence 4 Pro 120, the NF S12B as a fan that is not that great. And the T30 has another steep drop off, levels out, and then drops again. So we're noticing a couple trends with some fans where they drop off steeply and then kind of level out and then drop off again. The Squama does okay, but it is kind of bottom of the middle of the pack, so it's a bit on the noisy side for what kind of performance we get. How are we looking at 100% PWM fan signaling? Well, once again, we are towards the bottom of the graphs. So it's not in a great position with compared to my small selection of fans that I consider representative of different fans in each section of the category. Mind, it's not the worst until you're looking at larger cases, but it's on the bad side for small, medium cases. How about at airspeed versus decibels, and this is at the 9-inch mark. So if we jump back to one of my graphs, the 9-inch mark is where fans tend to start dropping in performance before they just completely tank. So it's not perfect for every fan, so like the Squama is an exception. It starts tanking at the 11-inch mark, and we see that in the next at the 100% as well. So the 9-inch mark is just where I found most fans start dropping in airspeed, but of course not every fan is the same, and it's you can't account for every situation. So that's what I have chosen it to be, just for simply sake for the review process. So it isn't at the bottom of the graphs. There's many fans that are underneath it, but its line is much flatter than many other ones because it starts off actually doing moving a lot of air, so airspeed vertical, noise horizontal. So it starts off moving a solid amount of air for its given noise value. And I almost forgot, note that every 10 decibels is a doubling in noise volume. So if a line might look linear as we travel along, it's really not. It's just fitting it on a graph is very difficult. So 10 decibels versus 20 decibels, that is twice as loud at 20 decibels than it is at 10. So 5 versus 15, same thing. 15 decibels is twice as loud as 5 decibels. So the Squama actually starts off really well for its given noise value, but its line stays relatively flat. It's not gaining much airspeed for how much more noise it is generating. While most other fans tend to kind of accelerate up at a much steeper angle. Heck, even the T30 starts off really, really bad, and then it just climbs and climbs and climbs and climbs, becoming much more efficient noise-wise as its airspeed improves. And if you're wondering about some of these fans that have little joggles, so like the Squama has a little joggle here, and we see a little joggle right there on the TLG12. That's where I hit a harmonic frequency either in the fan or the fan acting in my testing apparatus, which is why I'd like to upgrade the testing apparatus. Right now it's made out of cardboard and plexiglass, which is fine. It's sufficient for doing overall testing. However, I'd like to make it out of more solid material to better emulate or simulate a real case. So what do I say about the Squama? Overall, it's just not as efficient a blade design. Next up is testing through my Superior Air Cooler, which is the U12A, RPM versus airspeed. On both these graphs, better fans are going to be sitting top left, worse fans are going to be sitting bottom right, and this is just in comparison to my control fan. The first graph on the left side is airspeed versus RPM. This is basically a blade RPM graph, or not RPM, efficiency graph. It's how good is this blade design at moving air for a given RPM. In general, better blade designs would move more air for a lower RPM, while worse blade designs would, again, kind of be the opposite. So what are we seeing? The Squama is actually a fairly good blade design. It is sitting right around my control at the upper end of its RPM range. It is outperforming my control fan a little bit. but it's overall not that significant, especially when we start taking a look at the right graph. The right graph is airspeed versus noise. And right away we see that the Squama is, except at the absolute lowest, just completely demolished by my control fan, especially at higher RPMs, higher airspeeds. It is just not noise efficient. Where is that noise sound coming from? I can't say for certain. I haven't been able to devote time and resources into doing that sort of deep dive test methodology at this point. If that's something you'd be interested in seeing, please leave it in the comment section down below, and I'll look into starting to look into that kind of testing. But I surmise that it's actually within the motor. I think it was a little bit on the noisy side. But either way, that's how this fan performed. Next, how does this fan compare against every other fan? The Squama is highlighted or circled in yellow. And I want to do a couple other notable notes. My CPU air cooler is the U12A, which is a 120mm class CPU air cooler. My CPU is an 11700K Intel i7. And you'll notice these numbers on the side in this key. This is a wattage, 250 watts, equals an airspeed, 3 meters per second. So I did a series of tests on my cooler, and I have a whole piece on it where I have one fan blowing through it, and it's how much airspeed traveled through the cooler to equate to a given wattage. So approximately 3 meters per second of air going through that specific cooler for my specific CPU gives me 250 watts of cooling. And you can see where other air speeds line up. So the Tough Fan Turbo 12, or Tough Fan 12 Turbo, was giving me 1.5 meters per second of air. That's good for 210 watts of cooling, which means in theory my CPU could draw 210 watts and for this given noise normalized airspeed. Realistically, there might be slight changes because every fan blows air slightly differently, but it would be approximately that amount. And so how can you use this data? Well, if you don't have the same CPU as me, you don't have the same cooler as me, well, how can you use the data? Well, if let's say you have the NF-F12 on your cooler and you like my noise normalized values, well, it's only going to be moving 0.5 meters per second of air. If you upgrade to the Squama 2503, you're going to be moving 0.9 meters per second of air. So you're jumping from 130 watts to 155 watts. Or if you upgrade even higher to, let's say, the T30, you're going to be moving 1.3 meters per second of air. So you start to see some scaling. But if you don't have the same CPU as me, your wattages may not line up perfectly. And if you don't have the same cooler as me, your wattages are not going to line up perfectly. But what I can say is going from one of these fans that are towards the bottom to one of these fans that are towards the top means that you're going to be able to have your CPU run at a higher wattage, assuming it's unlocked, or it could run cooler if it is locked, and so you're not as high near that thermal constraint. Or you can take this extra overhead, so this extra 0.3 meters per second, you can back off the PWM fan signal till you get to the same level that you were with whatever fan you're replacing it with. And now your system will run even quieter. So if you're extra noise sensitive, you could buy a more powerful fan and then back off it, and it'll be quieter. That's how you can use this data to apply to your own system. And that goes for our 100% PWM fan signal graphs as well. You can apply it the exact same way. So how does the Squama rank? Well, it is bottom middle of this graph, I would say. So we have the fan name, the RPM was running, and the noise level it was generating. And once again, I want to note that airspeed measurements are plus or minus 0.1 meters per second. But due to repeat testing, I can verify that all the fans are in their proper place, even though fans that are within 0.1 meters per second of each other, that's plus or minus, could be considered functionally equivalent. And noise levels are in a plus or minus 4 decibel range. So fans that are technically within 4 decibels of each other could be considered functionally... New testing methodology, fans that are within 2 decibels of each other could be considered functionally equivalent. So that's a 4 decibel range. Remember what you're talking about. So the Squama here is in its position, and it's okay. It's a bit on the noisy side for its performance. The Storm 120 is significantly quieter for a similar level of performance, actually slightly better performance. But it's up to you to determine what kind of fan styling you want, and if you're willing to give up or sacrifice characteristics within it. Next is its performance versus airspeed performance versus noise through the CPR cooler. The Squama is towards the bottom of the graphs. It's really not that great. So I have a small selection of fans in here. So the SilenWings 4 Pro, the Arctic P12 is in here, the Tough Fan 12 Turbo, the General Typhoon. So all these are generally considered very good fans in their own right. So I felt that it was a fair way to compare Squama against it, basically going, hey, these are good fans, let's see how it places, as opposed to just trying to do a selection of bad, good, medium.
And this is the RGB look of the Squama 2503B, and this is a very subtle RGB effect. I think it looks absolutely phenomenal. Just that subtle little ring around the outside with the dimpling, I think it looks absolutely fantastic. If you just want a little touch of RGB and not it to just be lighting all over my case. I absolutely love the way the purple looks on this. My personal build is a purple and orange preferred setup in the coloring. And I really like the way that purple looks, much better than the way it looks behind. But let's go ahead and turn off the synced lighting so that you can see how the color changes and shifts all over. And that is a very smooth looking transition. I physically cannot see where any of the RGB lights are in it, which kind of is a testament. Not RGB lights, the LED lights. That means that there just must be a lot of them to make it that seamless a transition. From the back, it's the same sort of thing. It's a very subtle lighting. The posts are pretty narrow looking from the back, especially with the RGB LED lights. Overall, I really like the way this appears with its lighting effect. If you're not wanting something over the top. And at this stage in my life, I would say I prefer it to be not over the top. So this might be a top contender if I decide to do a pure RGB build.
Next up is my CFM testing. So CFM testing is probably my least favorite test in terms of what information you gather from it. So in essence, when you do CFM testing, so CFM is just cubic feet per minute. I run my CFM test through a cylinder. You know R, the radius. Actually, I know the diameter divided by 2. You know the radius. You square it, you multiply by pi, you have the surface area. You know how fast the air is running through that tube. So that's whatever unit of measure, meters per second, feet per minute. Let's just say feet per minute. You know the foot distance of the tube. So that's feet squared times feet per minute. So feet times feet squared is feet cubed per minute. So cubic feet per minute. Hooray! We did maths. But seriously, that's how it's actually calculated. And unlike in this picture, I couldn't find a good diagram. My fan is the exact width of the tube that it's blowing down. So it's smack right against the tube. And the air is blowing straight down the tube. So there's no room for the air to spread out. So even if a fan has a tendency to shoot air off to the sides, there's no room for it to go out to the sides. So the air is just going to travel down the tube. So this means that since all the air is wanting to travel down it rather than off to the sides, it has a better way of hiding the fact that the fan has a tendency to blow air off to the sides rather than in a nice tight pattern. So the two types of fans are going to look much closer in performance than they otherwise would, which is why that KISS simulation test is so important, which is why I insist on using that. A lot of other reviewers use just CFM blowing air down a tube to do their measurements. It's much more limited in its use cases, which will bring me to my point of how can you use CFM data and use it properly? Well, the first way is if you're using it scientifically. So if you want to generate PQ curves for airspeed versus pressure, how good is this fan at dealing with those sorts of situations, you can use this sort of test. Matter of fact, it's very applicable to that. Noctua is known for using that. And it just allows you to check different pressure scenarios. So different density fin stacks versus high density radiators. You could use that sort of data with a, basically you would have a flat plate with a little hole in it and how much airspeed is going through it. And you can measure the air pressure going through it. And you get all this data. The other way to do it is how the air is flowing. So I just mentioned heat sinks and radiators, how the airspeed is actually traveling through the heatsink or the radiator. You could measure the CFM going through that because you know the area coming out the other side. So you could calculate at a CFM rather than airspeed like I did. Both are perfectly valid. And the last place to use CFM would be total airflow through your case. So if you have one exit, so whether it's out the top or out the back, as long as the air is, generally speaking, not going out through any other part, just through the top or just through the back, you could measure the CFM or the air speed coming out that port, that hole, whatever it is in the case, and you could get a generalized total CFM for your case, but not per fan. And the last place it is valid is if you want to make your own at-home wind tunnel. So that's a lot like doing the CFM testing with the PQ curves. You could make a wind tunnel with a fan, blow air through it, do scientific measurements. Hooray! We got data! But in effect, I'm serious. That's what you would do. You could have a little wing section in here, measure airflow. But that's when you would calculate CFM and airdrops or whatever you wanted to measure it that way. So you could know how good the fan is that you have for your wind tunnel there. So now that I've ranted a little bit about CFM testing and how many channels that do fan testing just don't understand fans, because that's what they're using for case airflow tests, let's talk about what we're seeing. So it's very similar to what we talked about with the CPU or cooler one. Better fans are going to be top left, worse fans are going to be bottom right. This is CFM or airspeed for RPM, airspeed versus noise level for the right one. And we're seeing that the Squama closely matches my control fan, which is what we saw previously. And in noise testing versus the CFM value, we see a very similar result, except it looks substantially worse. So this brings me to my point with my current CFM testing. I would like to get a better testing apparatus. There's a website called HW Cooling. I actually really like their testing apparatus. It's this conical tube that narrows at the back, so it allows them to test a wider variety of fans. That's what my end goal would be. So I could do CFM testing for up to, well, 180 might be too big, but 120s and 140 millimeters certainly all on one testing apparatus, because the more fans that you can relate to each other, the better your data set will be. So you can talk about comparing 120s and 140s much more easily. With my current test methodology, I can only do on CPU coolers and in cases, but adding one more set of tests to directly compare them would be ideal for me. But right now, testing apparatus for 120s and 140 millimeters are different, and it's a short little tube with the anemometer sticking at the end of it, which means it's acting more like a pressure simulation case and scenario as opposed to more of an open airflow scenario, just because the anemometer fills up most of the space and creates, I believe, some back pressure in my CFM tube. Anyways, how does the Squama compare to a sampling of selection for noise normalized CFM testing? Well, it's ranked towards the bottom. We did see its generic placement earlier at the very first section, so you can always go back to that if you want to know how it ranked total, but it is towards the bottom overall. There are many fans that are just better at CFM or total airflow than the Squama is. At 100% PWM fan signaling, it is towards the middle of the graph. Once again, we have the fan name, RPM, and the decibel reading. Last up is CFM versus decibels across its range of, well, full RPM PWM fan signaling, how much airspeed does it generate per noise, or vice versa, depending on which way you want to think about it. And it's pretty similar to what we saw through the cooler, where it's more or less just a flat line. It doesn't gain that much airspeed performance at noise levels. So it's pretty flat. You see peak right there where it gains efficiency, but then it flattens out again. So overall, I like the aesthetic of the Squama, but I just don't think it's that good of a fan overall. So if giving up the performance for the aesthetic is worth it to you, you certainly can buy it. Next up is the value proposition. The Squama 2503 is a $20 fan, and it does come in a 3-pack, so you multiply 20 times 3, and it comes in a $60 pack. So it is a bit on the expensive side, and value proposition is a really simple calculation. It is just dollars divided by its performance, so that's airspeed or CFM. And overall, I would say the Squama is sitting right about middle of the pack. So we do have some major peaks, but you'll see some low, higher performing fans being at almost 1-to-1 in effect. So instead of like 0.87, while the TLG12 is really high up there. So if you're trying to pinch every penny to get the absolute best performance you can per buck, this is where these graphs are of utmost importance to you. Because if you're on a tight budget and you picked up a freebie case, freebie cooler, the fan on your cooler went out and you just need something to get yourself going, this is where you'd really be paying attention to value. If you've got a little bit of extra money to buy yourself something a little bit nicer, quieter, more performance, or you want a little bit of RGB, then you take a look at these graphs, compare it with the earlier data, and pick out which one suits your needs the best. So we already established that the Squama is sort of bottom middle of the pack in terms of its value over here. And at 100%, I would say it's kind of top middle of the pack. It's definitely outperforming more fans than it isn't in terms of its value, but it's just a far cry from the best value fans on this graph. And this again is for the 6-inch mark, noise normalized, and 100% PWM signals. Next, at the 11-inch mark, I would say that the Squama is underperforming quite a bit. Well, maybe not quite a bit in terms of its value. There are many fans that were just utterly terrible at this value, at the mark. And again, we're specifically talking about noise normalized. But the Squama is okay. It's not garbage. At the 100% PWM, the Squama is bottom middle in the average. But it's just so far from the peaks that it's just not a great value. Next up, CPU cooler testing, and same sort of what we're talking about with the just case airflow test. It's bottom middle of the pack, so it's okay. At 100% PWM fan signaling, at least it's kind of over average, but it's still kind of a far cry from the best fans, so it's just sort of generally okay. And last but not least is CFM testing, and we're seeing the same sort of trends overall, so no need to really talk about it. So I think the Squama with this RGB ring around it is a truly beautiful looking fan. Matter of fact, it's one of my favorite looking fans that I've tested. But generally speaking, its performance is not quite there where I would expect it to be to want to use it, unless just every other RGB fan out there just blew it out of the water. And I am in the process of putting together the data set for doing an RGB only quick roundup for comparing them just directly against each other as opposed to RGB and non-RGB. So I think it looks cool, but I personally just wouldn't get it for the case airflow testing, or case airflow. or radiator heatsink. It's just a little bit on the noisy side for me.